I have some particular goals in mind. There's of course a continuation of the discussion from yesterday, but also at least one proof I wanted to work through with someone. Am I streaming? I am streaming. Where's my live stream? Ah, there we go. Must be lagging a lot today. So, what are these problems we're going to have to get to? Well, people who regularly attend my stream will know that well, yesterday there was the other day there was a challenge I put to a certain viewer who claimed they had certain skills, and that viewer did email me, and their proof was certainly not correct. And so, good morning, Nicole. Good morning. So I am going to, for some of you, this might, I don't know, be fairly straightforward. But you know what? I talk about things that are way too advanced sometimes on here. Well, there's no such thing as too advanced, but you know what I mean. I feel like there's other things. So we are going to prove that there is a bijection between the following two sets. One is so set functions from the Cartesian product of A cross B into C, and set functions from the Cartesian product from A into the set of functions from B to C. And so we're going to do this by explicitly constructing two maps which are inverses to each other, because of course this is the superior way to provide a bijection, as opposed to just proving it's injective and surjective. So how do we do this rigorously? Well, first we need to define both of these functions. So let f be a function which goes from the Cartesian product of A and B into C. Then we need to, what do we need to do? So let me make a side note here to just explain how we're going to do things, right? So f goes from A cross B into C, right? And I need to provide a function that goes from A into functions into B into C, right? So that means this target, if I apply my map phi to f, it should be one of these functions, which means that for every element A in A, now this thing should be a function from B to C. So, hey, Dead Star, we're proving that there's a bijection between these sets of functions. So A, B, and C are all sets. Curry is a dish with sauce or gravy seasoned with spices. True, I agree. Is this a pun because this has to do with like curry Howard or currying? I mean, I love curry, the food, and I love currying, the mathematical concept. Apply. So this thing here has to be a function from B to C. So what does that mean? I need to, if I evaluate it at, I need to tell you what the value of this function is at B. So how could I do such a thing? Well, remember, f was a function from A to B, right? So I could define this function. F already tells me how to eat a pair, A and B, of numbers, or not numbers, sorry, of elements, and spit out C. You haven't had curry the food? What? How have you... How old... How? How is that possible? You need to go remedy that today. That is your homework. I'm personally assigning you a homework assignment to go and try it. Yeah. I mean, it's like anything. You can have. I'm sure you can find bad curry. You can find bad versions of any food anywhere. But you should try it. It's good. When it's good, it's real good. Hey, what is meant by an homomorphism on an arbitrary set? I just mean a function. I just mean a function between sets. That's all I mean. That's all I mean. So from our rough work, we can define phi f of A. So maybe we can define phi f such that, you know, for all A in A, for all B in B, phi f at A, which is a function. Can I be even more precise here? Yeah, let's be even more clear. So define such that for all A in A, the function phi f at A is given by phi f phi f A equal to FAB. Right. And there's not so much to prove in this case because that is a function between the prescribed domain and codomain. Sort of. I mean, this is a baby version. This is a baby version of the tensor Hom adjunction, because we're just thinking about sets. And so now, conversely, to come up with the opposite direction, you know, do I understand stone check compactification? Oh, it's been a hot minute since I've looked at it. Let's say no. But yeah. For this Cartesian closed category, yeah. I mean, surely it works in general, right? There's probably a general theorem about having like a monoidal, symmetric monoidal tensor category or something, right? But now let's think about how to construct the opposite direction. But we'll come back to stone check compactification. Maybe we'll look it up and discuss it together. We also have our homework that we said we were going to do about the relative differentials of a number field. So we can't forget to do that. So suppose we had some function now g that was here, and now I need to cook up a function from the Cartesian product into C. Is this not almost trivial if you understand a function? That's true. That would be the more rigorous and precise way to do it. Yeah. But I mean, the reason I'm talking about this today on stream is because a viewer, oh, good morning, Nerd Coke. A viewer sent I challenged a viewer to prove this statement to back up some of their claims about their abilities, and they did not send a correct proof. But I want to help them and set them on the right path. So I've decided to go through this proof in detail so that they can see what a proper proof would look like. So I should probably highlight the fact everything to the right of this bar is not part of the proper proof. It's just part of the rough work and the explanation. The actual construction is over to the left of this bar. Okay, so somehow I need to eat a pair of elements A and B, and to return an element of C. Well, G, right? G is a function that, at least if you plug in a value of A to it, you get out a function that goes from B to C. So that, in turn, can be evaluated at some B. And there we go. That'll be our definition. So similarly, for G in HOM A, HOM B, C, define psi G from A cross B to C by psi G A B, defined to be G at A, G at B. They're different ideals. Now you understand geometrically how we define the ramification locus as a support of relative differentials, but Neukirch says annihilator. Perhaps they agree. Well, we can dive into it. Yeah, I mean, an annihilator is somehow the dual of the support or something, right? So now what do we need to do to complete this proof? Well, we need to prove that, good morning, Luis. As the weeks draw closer to the start of your master's, you don't know whether to feel like a fraud. You should feel like a fraud because everyone in grad school feels like a fraud. Maybe not everyone, but lots of people do. It's called imposter syndrome. So, the greatest thing I ever saw about imposter syndrome is someone was like, "Oh, just lean into it. Just spin that and go, ha ha ha! I fooled all of these people into thinking that I'm worthy of being here." And I don't know. I thought that was interesting advice. I feel like a fraud for going for a pure math. The problem in India is that there's no applied math courses in India, so you'll probably apply abroad. Yeah, well, you know what? There was once upon a time, other people were doing such high-level stuff that I couldn't understand. And there's still high-level stuff that I can't understand, but less of it than there used to be. So what do we need to do to establish that these two maps form a bijection? We need to show that they're mutually inverse. So let's prove. So for example, to prove that psi composed with phi of f, we need to prove that both compositions are the identity. Is the identity. Hello, Suas. We're proving a bijection between sets. We're almost through this, and then we're gonna switch gears. So just give me 1 second here. It suffices to show that for all AB, right? The thing is, we're just trying to show that if I plug in some function f into psi composed with phi, then I get f back, right? So it suffices to show that for all f from AB to C and AB in A cross B. Honestly, you try to keep up the past few weeks, but you're exhausted and feel like you haven't learned about many things and think you've learned about many things but do not understand anything deeply. Well, A, take a break. If you're exhausted, take a break. B, focus on the basics. Just really make sure you hammer home the basics and you know the basics well. That's most important, to have a strong fundamentals. So it suffices to show that psi composed with phi of f as a function evaluated at AB is simply equal to FAB, right? That's what it means. That would show to us that the function we get out from this composition is the same as the original function. So we simply need to do this computation, right? So we could view this as psi of phi applied to AB. But remember, our definition of psi took the function as input and evaluated that function at A, and that function we evaluated at A, remember, is supposed to be a function from B to C, and so we then plugged in the value B to that. So we plug in the value B. Then, if we think about, so I'm not going to scroll back up, but you can remind yourself that the definition of this function f at AB was, in fact, actually just FAB. So that proves the claim. Okay, I'm going to leave it for the person who this question is for to verify on their own that psi composed with phi is the identity. And once you did that, you could complete the proof. Okay, this isn't the only way to prove it. You certainly can get away with just writing down one of these functions and proving it's injective and surjective. I don't think this person will understand the suggestion from Alakeen in chat, but I absolutely love this suggestion. That it's to use the actual formal definition of a function as a subset of the Cartesian product. Beautiful. Okay, what are we moving on to now? I guess now we move on to the algebraic number theory. No, wait, someone else had a question. Oh, what was the other question? Stone check compactification, right? Stone check compactification. Aha. It's like some sort of universal. It's pretty big, isn't it? Generally, the stone compactification is pretty large. Technique for constructing a universal map from a topological space to a compact Hausdorff space. The stone check is the largest. Well, there you go. Most general compact Hausdorff space generated by X. Good morning, Julie. In the sense that any continuous map from X to a compact Hausdorff space factors through. Just draw me the commuting diagram, gang. Come on. Where's the commuting diagram? A form of the axiom of choice is required to prove that every topological space has a compactification, even for quite simple spaces. Interesting. Huh. Yeah. Maybe I've never. No, maybe I haven't really. Maybe I haven't really studied the Stone-Check compactification, actually. I don't know if I've ever actually done any serious computation or proofs with this. But if you had a question about it, new wave infantry, we could talk about it. I might not have helpful things to say. You also have a probably basic category theory question that came up in some analysis. Ooh, that sounds cool. That sounds cool. I am going to start setting up this algebraic number theory question, but feel free to do that. While you're maybe typing that question, I'll just get us going with. So let's just look at this simple example, everyone's favorite field extension, and recall that our in our ring of integers, up top, I don't know, O. You got Z. The prime 2 ramifies, splits as a product of this prime ideal, and then the rest is controlled by being a sum of squares or not. So 3 is inert. 5 splits as a product of primes. 7 is inert. And so on and so forth. Yeah, very cool stuff. Something, Pythagorean triples, something. Okay, so right. So we have this one prime that ramifies. So our ramification locus should be a single point. So what does Neukirch say about this? Where are we here? Aha, the different is the annihilator. Right, it's the annihilator of this module. So let's go up and let's remind ourselves. Right, what is the official definition of the Collar differentials? I should really know this by heart, as someone who claims to be a geometer. For arbitrary extension of commutative rings, the homomorphism, and then the kernel I, it's I mod I squared. Okay. So it's x, y to xy. So let's work that out. Where'd chat go? So we've got our map. Mu will go, in this case, I guess our B is O, and we're tensoring over Q, and we're going down, we're going into O, and we're mapping, we're taking X tensor Y and mapping it to X times Y. Is that right? Yeah. And then we want I to be the kernel of mu. And then our relative differentials will be I mod I squared. Okay. Okay, so here's the category theory question. Pretty much concerns a category of Hilbert spaces. Loosely, the statement that there is no tensor product in the category of Hilbert spaces. Proof has something to do with universal properties. Interesting. Is there not? I thought there's a way to make a tensor product. Let's put this discussion up here. I thought there was a way that like you take some like You take the ordinary Hilbert, you take the ordinary tensor product, and then you take some like Hilbert space completion. I thought that was possible. Um, uh, of non-existence of tensor products. Paul Garrett. Paul Garrett, by the way, another goat of education in the Langlands program. I mean, he's also done serious work in the Langlands program. Let's not get it twisted, but also has a lot of great articles to learn from. So let's see, non-existence of tensor products. Paul Garrett. That's interesting. I mean, I could still believe. So even though I'm pretty sure there is some way to take a Hilbert space completion, I could be wrong. It definitely makes sense. Like the Hilbert, like the tensor product, the usual tensor product of vector spaces satisfies a certain universal property, and I could definitely believe that it just turns out that this doesn't satisfy a universal property. Actually, maybe infinite dimensional things like is what are messing it up. Your intuition is for a map of curves, each fiber has finitely many fat points, and only non-reduced points would contribute to the relative differentials. Maybe. I don't actually know. The statement of Yoneda lemma that you've seen in a topology book is right, that isomorphism of sets where f is a functor and nat is a collection of natural transformations. Yeah. But to be honest, you don't see why it's super important. Maybe because you haven't seen it out there yet in explicit fashion. Yeah, let's come back to that in a second. We're not supposed to use Collar's name anymore due to his ideological views. Oh, I don't know about his ideological views. Well, okay, I mean, there's a whole question. Okay, there's a very interesting rabbit hole political discussion we could get into of, whether we do that or not. Do we stop using someone's name for something? Should we? Could we? I could definitely I could definitely be swayed for the argument for yes, of course. Don't want to put respect on someone's name who doesn't deserve it, in a certain sense. At the same time, I think it's very hard to change things that are deeply ingrained, especially when all the old textbooks, say this and everyone knows it by this name. Now, is that a reason to not try and to not be more mindful? I guess. There's also a whole discussion of like, well, should we really name theorems after people? I mean, it's nice to honor people, but also it's like, well, what does math really belong to anyone? And what are we going to keep doing, like memorizing names? What about 4,000 years from now? How many names will one have to remember that don't tell you anything about what the theorem is about? Okay, anyways, I'm just saying there's a lot to discuss there. So for the purpose of the stream, I'm probably just going to keep call it Collar, but okay, I could be convinced that I shouldn't. Hilbert-Schmidt completion works, but you don't understand the universal property aspect of the proof. Also, the first footnote in the paper is of philosophical interest. Where is that? The first footnote. Many of us are not accustomed to worry about the existence of objects defined by universal mapping properties because we construct them. I'm not sure I understand. Yeah. But can you guys hear my roommate yapping in the background? Oh, maybe he stopped. Okay, so the conclusion, let's see, right. The conclusion is there is no tensor product of infinite dimensional Hilbert spaces. Interesting. Yeah, I don't know. I guess I might have to read this a little more closely. I might have to read this a little more carefully. But it's important in practice. Yeah, I guess this is maybe a slick idea to. Yeah, okay. I'll have to take a look at this. I mean, if we look back on people with our standards, lots of them will fall. Even maybe especially recent math guys. Cantor also comes to mind. Really, I didn't know. I didn't know anything about Cantor being sus. Yeah, I mean that is true. Like, I think that is true. Um, but I don't know. It's complicated. I think just because you can look back and say, oh well, you know, pretty much anyone from the past wouldn't live up to our modern expectations. You could just throw up your hands and say, well, it doesn't matter at all. And I don't know if that's the right approach. Um, but I mean, it is true. Like what Newton, Leibniz, all of these like even though we don't hear about explicitly terrible things, like I'm sure maybe Collar did significantly worse things, but yeah. Well, I'll take a look. Hello, Femno. Yeah, Nerd Coke. I'll take a look at it. Maybe over the next couple days. I'm gonna be really busy, but um, my well, here, let me give you a recommendation. So I think the reason why the universal property of the tensor product shows up is I think at a glance, I think the idea is to basically just show that maybe do like a proof by contradiction or something, and just show that there can't be something that satisfies the universal property. So if you're getting confused on that part, I would maybe go consult. I would go consult, say, Alufi, and in particular the tensor product, the section on the tensor product of modules, where he goes through both the construction and the proof of the universal property. That might be helpful, but maybe I'll have something more useful to say on this tomorrow. But that's interesting. Okay, so is this where we were in the discussion? Yeah. Okay, so what are our relative differentials then? Well, I suppose. Well, kernels and tensor products are a weird thing. Mind you, I guess this is these are all I guess these are all Q vector spaces. Yeah, no problem, Nerd Coke. No problem. These are Q vector spaces, right? So this should just have a basis. Yeah, Luffy's the sledgehammer for any algebra question. Well, maybe there's more comprehensive books than a Luffy, and a Luffy is also more a self-study book than a reference book. But yeah, that's my default reference for everything algebra to anyone. Right. So a ring of integers should just be z adjoin I, right? Oh, right. Yeah. So, oh, sorry. This isn't a tensor product over Q. What am I saying? This is a tensor product over Z. This is a tensor product over Z. Aha. Right. Yeah, but we don't want the differentials. We don't want the. It's not that ring. We're looking at the differential, the relative differentials of Z adjoin I over Z. So, but I still think this will be like a free Z module, right? Because basically what are things in this ring? They're like a plus bi. They're like integers of this form. Tensor c plus di. So certainly this will be generated by this over the by these elements as a z module. Yeah, and it's got to be free, right? I'm pretty sure. So that should make our computation easy, right? So well, let's figure out what the kernel is. So 0 equal to mu at a plus bi tensor c plus di. Well, that's just going to be the product of a plus bi and c plus di. And, well, this is an integral domain, right? So that's only possible if both of these terms are 0. Or, sorry, if one of these terms are 0. Over any polynomial ring, over any base ring, mod and ideal. Yeah. Yeah, I mean, I guess, right. I guess this is zx mod x squared plus 1. There's probably some general fact we can use there. But whatever, we're deep in this smooth brain level computation. What are some of my favorite self-study book recommendations? Well, definitely a Luffy when it comes to algebra. I don't know. I don't know what else. What else particularly strikes me as particularly good for self-study? Yeah, I don't know. I don't know. I don't know. Oh yeah, I guess this means this map is inject. I guess that would mean this map is injective. Wait, does that mean our kernel is trivial? Does that mean our relative differentials is trivial? That can't be right. Can it? No, I must be tripping. What else is good for self-study though? Yeah, I don't know. I mean, I feel like most textbooks are just textbooks, and they're fine either way. Right. Can this be right? Certainly, I've done something stupid, right? Arbitrary extension of commutative rings. Yeah, we took that homomorphism. We computed the kernel. Atia McDonald commutative algebra is nice for self-study. Yeah, that's true too. Actually, Atia McDonald does have a nice mix of. Atia McDonald does have a nice mix of. What am I trying to say? Like, they put, some exercises, some things that, like, there's a mix of, like, pushing things to the exercises. Oh, yeah, and of course, Ravi Vakil. Sure, yeah, it's pretty big, but also, yeah, Ravi Vakil's, his book's really good, too, because the exercises are all labeled in terms of, like, difficulty and how important it is for you to do and whatnot. Oh, hello, nerdy Quagsire. Hello. Well, now I'm concerned. I've been doing something really stupid. Am I ready for today? The day, generally speaking. I'm always ready. I'm always ready. I'm ready even when I'm asleep. I'm always prepared. So don't forget that. Uh, can Ravi Vakil replace Hartshorn? Yes, and it should. You have a much better time reading Ravi than you will Hartshorn. Yeah, maybe I'm done. Maybe I should have just done this computation. Maybe I should have just done this computation. But what is going on? There's how could I possibly how could I possibly be wrong about that? I mean, it is an integral domain, right? So um, uh, AC minus BD plus AD plus BCI. Harshern is mid. Vakil the goat. Yeah. Yeah. I mean, Hartshorn's still a great book, and it'll always be the cultural cornerstone. It was the first, I think, one of the first serious efforts at an algebraic geometry textbook since EGA and SGA, which were supposed to be like exhaustive references, basically, that built the entire theory. So let's not, let's not forget everything that Hartshorn gave us. But Vakil is the future, or at least it's the present. Hello, Beastmaster. Yeah, I mean that is true. That is true. Yeah, Vakil maybe leaves more stuff to the reader than Hartshorn. Although Hartshorn doesn't not leave things to the reader. And some exercises, at the time of printing at least, were unsolved. But that's maybe what makes it even better. But Vakil definitely is better for self-study. It'll always be, how long did you take to solve all the problems in Hartshorn book? Yeah. Yeah. Although, who knows? Maybe when we get good enough at understanding, infinity categories through the theory of cosmoi, we'll be able to just teach that approach to undergrads, and we'll just circumvent, like, literally all of that. I mean, I guess it makes sense. We shouldn't have like differentials, because these rings are just stupid rings, right? So I could believe that we don't have differentials. Um, but then I'm really confused as to uh, I'm really confused as to how we're going to get our one ramifying prime out of this. But let's just trudge ahead boldly and look at the annihilator. I mean, the annihilator has to be everything, though, right? The different. Maybe that's fine. Maybe that's fine. So uh, the different has to be the annihilator. The different, this is going to be all x in zi, such that x dy is 0 for all y in zi, I believe. Did I copy things down correctly? And that's big O, right? Yeah. But I mean, so then, how can this possibly be right though? Because that would mean, if our relative differentials are just 0, that means this has to be 0 for all y, and so our different ideal would have to be the entire ring. And there just ain't no way, right? Wow. I love publicly failing on math on live stream. What is this? Where are you? Well, you're somewhere between the first name and the last name. What you are in, though, is an office hours for mathematics. Welcome. Oh, Jose, the ultimate goat of algebraic number theory, number one goat in the world, has shown up in chat to save the day. Note that your ring is commutative. See? Number one goat. Number one goat has come to save the day. Number one goat has come to save the day. Maps to 0. Aha. So. Where have I gone wrong, man? So I 1 minus 1I maps to 0. Oh, is it because... Oh, I'm such an idiot. I was just computing simple tensors. Oh, but everything should be a simple... Wait a second. Okay, let's just do this. So 1I minus I1 right. That's going to be... oh, yes, of course. Right. That'll be I minus I equal to 0. Right. Good thing that you guess everybody here is failing miserably at math privately every day, so it's not really embarrassing. Yeah, I mean... True. I mean, what do you mean? All of my subscribers are super geniuses, as am I, and we never fail, ever. Just kidding. Failure is like 90% of mathematics. Okay, so how did I get this? How did I get this so wrong then? Oh yeah, because see, Jose here is too humble. This is how you know someone's an actual goat, because they're humble. You know, there's people showing up in these live streams who are like, oh, I understand blah 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 blah, and then they don't when they email me their proofs that are incorrect. Actual humble people show up and they're like, they just quietly give the right answer once in the middle of stream, and then they're like, oh no, I'm not that smart actually. But yeah. Oh, and yeah, it looks like Arad is also gave that example. I guess I just messed it up. I might have missed. But I don't think. But you wrote but I don't think. Oh, you're right. I just did the math wrong. That also goes to 0. Yeah. So there's 2 Chads in chat. I was just so brain dead that I missed the first super Chad. Okay, great. So yeah, the answer was I was just being dumb about simple tensors. Okay, great. So then how can we compute the kernel? I guess maybe we could compute it in terms of this basis, right? So let's compute the kernel in terms of this basis. So let's go A plus B plus C plus D. Yeah, this is the way to do it. Let's say this 0 equals, you're right, everyone is a Chad in this chat. So 0 equals A plus BI plus CI plus minus D. This is fun. See, this is great. This is probably the ideal office hour between today and yesterday. Like, we collectively as a group are working through some problems together, if even in a smooth brain way, and that I think is beautiful. Right. So what is the so then this will only be 0 if D is equal to A and C is equal to minus B. So in other words, our kernel is going to be A. Good morning. Good morning, Super Baron. A times this plus B times, which one did I say B was? B was 1I minus B times I1 plus A. Best of luck, whatever this is. I'm glad you were here and confused like the rest of us, first name, last name, and I hope you have a good day. But I am sad that you're leaving us. Okay, and here goes an A. Great, so we figured out our kernel, and now our relative differentials is going to be I squared. Gosh, do I really want to compute the square of this ideal? It's probably not so bad, right? Do we need to work out the square of this ideal though? Maybe not. Let's see. As a much more advanced remark, I suspect the definition in terms of trace can be interpreted as Grothendieck duality, but you're not so experienced enough to work through the details of that wild claim. Possibly. I don't even... Grothendieck duality. Is that like Serre duality or something? Coherent duality of coherent sheaves? Serre, Grothendieck, Verge duality? Oh, well, Verge duality I know, sort of. That comes up in my work on like perverse sheaves. Oh, I see. There is some sort of tracing. And it's interesting actually. Our resident algebraic number theorist was talking with me the other day and told me that there's something to do with this unit, something to do with this natural transformation and it being called trace. Although I still don't understand what it has to do with traces. Very interesting. Yes, I want to compute it. Okay. Well, if you insist. But I am thinking, like maybe we don't need it because, like, I guess we still need to know if something is in the square of the ideal or not, and but we actually just want to know if some x annihilates the differential, the derivation. Consists of these linear combinations. Right, because we can just so I don't know, maybe we can get further. So let's take we could take this, right? So if we computed like an arbitrary y, so if we had some arbitrary y in here, let's just compute the differential first. Then the differential of an arbitrary y is supposed to be oh, what am I saying? I've expanded it the wrong way, sorry. Y is a plus bi. The differential of y will be y tensor 1 minus 1 tensor y mod I squared. Did I get the directions right? Yes, y1 first. Which works out to be a plus bi tensor 1 minus 1 tensor a plus bi plus I squared. Atrocious writing, I know. So what do we get? A tensor 1 plus b I tensor 1 minus a tensor 1 tensor a plus minus 1 tensor I. Maybe pull the b out in front. You think you'll drop an optional differential equations class and just leave the cool stuff and be happy this semester? Hey, you know what? I wish I had been more interested in differential equations when I was younger. It's never a bad idea to expand your mind, but also younger me sympathizes with your stance. The undergrad research stuff is getting cool, but time management isn't easy. Yeah, that's definitely fair. So, but I think we get some simplifications, right? Because this is, wait, did I do something right? Should there be an I here? No, yeah, these two terms cancel out. Unless I'm being crazy. Chat, y'all gotta help me. Hello, Matthias. I'm doing good. I think everyone else in chat is doing good. I hope they are. Yeah, so it should just work out to this, right? That should be the differential of an arbitrary element. And so now, I guess if we compute x, y, so let's now maybe write x like this, y like this, then x dy will be a plus bi times d. Yeah, there should be plus I squared here. Yeah. Will be d times I 1 minus 1 I plus I squared. Yeah. And now we want to check when this is equal to 0. When we want to check when this is equal to, is in I squared. So yeah, we might want to work out I squared. But my coffee's done. So I think that's going to do it for today. We'll have to keep going on this tomorrow. But this has been great. This is peak office hours. How little classes in a semester is too little? Good question. If you drop differential equations, I mean that changes, right? If it's year 1, less than 5 is too little. If it's year 4, I mean 3 math courses is a lot. If you drop differential equation stuff, you'll only be taking 4 classes, one being not strictly mathematical. I don't know if people care about this sort of thing. I don't think they care about that sort of thing. But yeah, I mean the question is how much do you care? Can you handle it, and how much do you care about finishing sooner than later? Anyways, that's gonna do it for today. See all of you tomorrow. Time to go